it can be shown that the acceleration of an object moving along a smooth curve C has both a tangential component and a normal component, where the tangential component is defined to be the derivative of the speed of the object, and the normal component is defined to be the curvature of the curve times the square of the speed. These are called the scalar tangential and scalar normal components of acceleration, respectively. So let's illustrate this qualitatively. Suppose we have a curve in space, and that this curve can be represented by a position vector that is formed from parameterized functions of t for the x, y, and z components. We know that the velocity of a curve is equal to the derivative of the position vector with respect to the parameter t. Furthermore, this velocity vector is a vector that is always tangent to our curve at any point. Well, let's pick one of those points on this curve. Let's pick a point right here. And right here, let's say we have our velocity vector, which is a tangent vector tangent to the curve at that point. Also, let's suppose that we have an acceleration of our curve. Now, acceleration, remember, is the rate of change of velocity with respect to the parameter t. So we could write that as acceleration is the derivative with respect to t of our velocity. So remember, velocity can change in two ways. Its magnitude can change, and its direction can change. With that said, let's illustrate an acceleration vector that is just an arbitrary acceleration vector. This will represent our acceleration vector right here. And actually, let's exaggerate this acceleration vector so I have more room to play with. Here is our acceleration vector as a function of t for this curve. Now notice, relative to our velocity vector, and again, the velocity vector is parallel to a unit tangent vector at that point. Relative to our velocity vector, acceleration has two components. We can see that more clearly if we draw a line on which the velocity lies. If we project a line directly from the head of the acceleration vector down to the line on which velocity lies, that line will be perpendicular to the line of velocity. If we then project our acceleration onto the line of velocity, we get a component of acceleration that is parallel to the line of velocity. This component of acceleration parallel to the line of velocity, we call the scalar projection of the acceleration onto velocity. More simply, I'll just say the component of acceleration parallel to velocity. And from trigonometry, we would get that to be equal to the magnitude of the acceleration times the cosine of the angle between the acceleration and the velocity vector. We have actually shown previously that this is simply the dot product of the acceleration with the velocity over the magnitude of velocity, which is speed. So in other words, this is a component of acceleration that is tangent to our curve. So let's write that down. The component of acceleration tangent to our curve is given as the dot product between acceleration and velocity divided by the speed of the curve. And let's signify that this is tangential by adding a unit tangent vector. So this is a vector that is in the same direction as velocity, but it's of unit length, the unit tangent vector. And remember, the unit tangent vector was just defined as the velocity of our curve divided by the speed of the curve, which is the magnitude of velocity. So we now know the tangential component of our acceleration. But if you look at our graph, there is also a portion of acceleration that is perpendicular to the line on which velocity lies. This portion of acceleration we could call the scalar normal component of acceleration to velocity, is given from trigonometry as being the magnitude of the acceleration times the sine of the angle between the acceleration and the velocity. I should go back and label this theta in the triangle with a subscript AV as well. Now, we've shown previously that this perpendicular component of acceleration, being the scalar component normal to the line of velocity, is equal to the magnitude of the cross product between the acceleration and the velocity divided by the speed of the curve, or the magnitude of the velocity, if you will. So this piece gives us the scalar normal component of acceleration relative to velocity. And we could describe that direction with a unit vector. So this unit vector will be a vector that is normal to the curve at that point. And this principal normal unit vector is defined to be equal to the derivative of our unit tangent vector divided by the magnitude of the derivative of the unit tangent vector. This gives us the component of the acceleration that is perpendicular to the line of velocity. So we could add that unit vector right up here into our equation. So now we have, relative to a curve, two components of acceleration, a component tangent to the curve and a component normal to the curve. Without much more work, we could show that the component of acceleration tangent to the curve is just equal to the derivative of the speed of the curve. And the component of acceleration normal to the curve is equal to the quantity kappa, which is the curvature of the curve, times the speed of the curve squared. We now have equivalent expressions for the components of the acceleration of a curve relative to the velocity or lines of velocity on our curve.